Hello everyone, let us understand the suction stress characteristic curve. Liu and Lycos in 2006 have proposed the concept of suction stress to consider the physicochemical forces and capillary forces due to surface tension in the air water interface and any other forces that are not considered in the previous study are included as suction stress into the effective stress principle. So, the advantage of suction stress is that it is valid for any given soil and all different forces are considered into the suction stress. Now, let us understand how this suction stress characteristic curve varies for different soils and how this is related to the soil water characteristic curve. So, the suction stress characteristic curve, how it varies etc., we will define based on how the soil water characteristic curve regimes change. So, if this is the soil water characteristic curve for a given soil, here y axis is UA minus UW, that is a matrix suction, and on x axis volumetric water content is given. Now, the SWCC curve varies in this particular manner. So, this is theta S, saturated volumetric water content, and the air entry suction value of this particular soil is somewhere here. So, this is UA minus UW AEV. So, this is UA minus UW AEV air entry value, and beyond that the water content decreases drastically with increase in the matrix suction, and the change in the water content starts decreasing with increasing in the suction after certain pressure, and beyond certain suction value it is very difficult to draw the water by increasing the suction in the soil. So, if this is a residual water content theta r, so if different zones are considered in this particular manner, in the first zone, so this is a saturated state of the soil even though the pore water pressure is negative, and this is the second stage where drastically the water content decreases with increase in the suction, and this is the third stage where the rate of the decrease in water content will start decreasing, and fourth stage which is a residual stage where water is held around the particles in hydration. So, this is a hydration stage where water is available as a thin film around the clay platelets. So, this is SWCC soil water characteristic curve. So, now the suction stress characteristic curve can be drawn. Here the x axis has theta volumetric water content. So, on the y axis sigma s dash. So, this sigma s dash is suction stress. So, how this suction stress should vary now? So, as we have the equation for the suction stress, that is sigma s dash is equals to change in the stresses due to physicochemical forces Pc plus sigma capillary plus xi UA minus UW. This is one of the expressions which was given by Liu and Lycos. So, this is not found in the textbooks. So, here in the first stage of soil water characteristic curve or the initial first regime, so the change in the physicochemical aspects of clays are insignificant because the change in the volumetric water content is very small, water content decreases very insignificantly, the change in the physicochemical aspects become 0. So, this aspect for the first regime the PC is negligible, change in the physicochemical aspects of the soil are negligible, and the capillary phenomena is also negligible in the first zone or first regime, where the water content is nearly equal to the saturated volumetric water content or the soil is saturated state. So, then you have Xi into UA minus UW. So, here Xi is also approximately is equal to 1, and whatever the variation in UA minus UW, you will see it in suction stress. So, therefore, whatever the change you see here, similar change you will see in suction stress. So, in the beginning, so in the first regime. So, beyond that, as in this case this is UA minus UW is less than or equals to UA minus UW AEV, air entry value. In the second regime, so in this expression where UA minus UW is more than UA minus UW AEV, so soil desaturates quickly and capillary forces would start increasing, and the electrostatic repulsion will start decreasing in the soil, and attractive force are nearly constant, provided the soil grains would not come close to each other, or the change in the pore size distribution does not change significantly. But if the soil desaturates quickly, then the van der Waals forces remain nearly constant, but then the repulsive pressures within the soil mass will start decreasing. So, this is insignificant, which is close to 0, but the capillary forces are significantly higher, they start increasing. So, their effect is nearly negligible. So, as this desaturates, the capillary forces would shoot up, and the contribution is essentially from the capillary forces. So, beyond this, in the third regime, where the repulsive pressures diminishes and the attractive force, if interparticles distance decreases due to desaturation. So, the overall increase will reduce because of this, and capillary effects also start diminishing, this starts approaching a constant value, and for sands this value starts decreasing because the capillary forces effect is also getting reduced, because the amount of moisture that is available in the soils is getting reduced, and the physicochemical force anyways are not significant in sands. So, therefore, for sands this will starts decreasing in the third regime. So, this is third regime, and in the fourth regime water is held as a thin films around clay platelets. The amount of water that is available in the soils is only available for hydration of exchangeable cations and hydration of layers of different inner layers of clay platelets. If it is you will have multi-layer hydration, that is the water equivalent to multi-layer hydration is available in clays, and a single layer of hydration may be available around sand platelets. So, the suction stress, essentially the capillary force are 0, and sigma Pc is anyways 0, and Xi reduces to very small value and approaches close to 0. In case of sands this goes to 0, but in case of clays, because the attractive forces or the van der Waals forces still exists, which gets a constant value somewhere like this. So, this is the suction stress characteristic curve of a given soil. This is for sands and this is for clays. So, it approaches a constant value somewhere here. Similarly, this same graph can be drawn for UA minus UW, there is matrix suction on x axis, UA minus UW on x axis and suction stress on y axis. So, initially the suction stress increases at the same rate as the matrix suction value. It follows 1:1 linear relationship, and beyond that the increase in the suction stress decreases with increase in the suction, and which becomes nearly constant at a particular time. But in case of sands, this suction stress decreases and becomes 0 at one particular matrix suction. So, this is for sands and this is for clays. So, initially there will be 1:1, linearly it increases, and beyond this is a nonlinear behavior and it starts decreasing and suction stress becomes constant, because the contribution of only van der Waals forces and such short range forces are dominant at that particular suction value. So, how to understand this suction stress characteristic curve? When we plot the strength, the Mohr Coulomb envelopes, tau f versus sigma n, normal stress, we get a failure envelope for saturated soils somewhat like this, and for unsaturated soils the cohesion intercept, the intercept value increases, it increases in this manner. This is the observation from the experiments, suction controlled either direct shear tests or suction controlled triaxial tests. These are the observations I have discussed earlier. This is a failure envelope for saturated soils, that is tau f is equals to C dash plus sigma f dash tan phi dash. So, this is angle of internal friction, this is phi dash, and this is C dash. And similarly, this is the envelope for tau f equals to some C1 dash plus sigma f dash tan phi 1 dash we can write, and this is another failure envelope C2 dash plus sigma f dash tan phi 2 dash. So, however, we have observed that the phi dash is equals to phi 1 dash equals to phi 2 dash from the experimental data, that all these lines are parallel to each other. So, this is experimental observation. So, the angle of internal friction is a metal constant, it does not vary or it does not depend on the suction, and which is constant. So, when we extend these lines back onto sigma n axis, so back onto this negative axis, this is this negative axis is your tension. So, when you extend this, tau f is 0 at this particular point. So, therefore, the sigma s dash is C2 dash by tan phi dash, and here the point is C1 dash by tan phi dash, and here this point is C dash by tan phi dash. So, if this becomes your matrix suction UA minus UW, that is a representation of negative pore water pressure within the soil. So, this particular value when you are drawing for a given matrix suction, this is done for one particular given matrix suction UA minus UW of say 2, and this is UA minus UW of say 1, and this is UA minus UW is equals to 0. So, this is for 0 and UA minus UW some particular value, and this is UA minus UW some particular value here. So, then the profile that you get is somewhat like this. So, this is uncorrected suction stress characteristic curve, and if this is corrected and made it to go from origin, then this becomes somewhat like this. So, this is corrected SSCC, suction stress characteristic curve. So, this sigma S dash is, this is for sigma S and this is sigma S dash, which is equals to sigma S minus sigma C naught. So, this is how the corrected suction stress characteristic curve can be obtained for any given for suction stress characteristic curve, or the effective stress can be determined for a given suction value using the measured data from suction control tests. When the data of deviatic stress Q, that is sigma 1 minus sigma 3 deviatic stress, or it could be tau f if it is a direct shear test. Q is a deviatic stress in triaxial test, which is equal to sigma 1 minus sigma 3 in triaxial test, and tau f is the shear stress applied on soil in direct shear. And on x axis you can either show sigma, the net normal stress, or it can be represented with P, which is a mean stress. So, the mean stress represented here is sigma 1 plus sigma 3 by 2, and here this is sigma 1 minus sigma 3. So, that is deviatic stress. So, then this is plotted, then you get a series of straight lines with nearly the angle of internal friction is equals to phi dash, but different intercepts for different matrix suction values. So, this is u minus uw increasing up. So, the strength is increasing for any given mean stress. So, this test data can be interpreted by computing obtaining the cohesion intercept, say for example C1, and for this one is C1 dash. Once this is obtained and phi dash is anyways is available. So, this particular point is C dash by tan phi dash, and this is C1 dash by tan phi dash. So, these values are available. So, therefore, these are the suction stress values, sigma S values. The matrix suction at which these tests are conducted is also known. So, therefore, UA minus UW axis is known, and these y axis values are obtained from cohesion intercepts, and therefore, the sigma S is known and UA minus UW is known. So, therefore, we can plot sigma S versus UA minus UW. This essentially the variation is somewhat like this, and also we can plot Q, the deviatic stress versus P dash, that is a effective mean stress. So, as we know the effective stress values, so therefore, we can compute the mean effective stress values, then you get a unique straight line. This itself is a failure envelope. As we could determine the true effective stress from the SSCC, we can obtain the unique failure envelope for different matrix suction ranges. Let us understand by an example problem. So, in this example we have data of, this is a synthetic data, a number of tests are conducted, test number, and the matrix suction, how this is varied or controlled, and this is mean stress, and this is deviatic stress which is observed at failure. So, this is test 1, 2, 3, 4. 4 tests are conducted at one matrix suction, that is 0. So, that means at saturated state these tests are conducted. So, the p values varied 130, 350, 520 and 695. This manner they varied under 0 matrix suction or saturated condition, and when the p net normal stress varies in this manner, then the Q value varies as 120, 274, 393 and 516, and another set under matrix suction value of 200 kilopascal are conducted. So, the value of P varied in this manner. And another set of data with a matrix suction value of 400 kilopascal are conducted. The P value varied as and last set of data the matrix suction is 850 kilopascal and the P dash varied as 238, 475, 650 and 838. Then the Q deviatic stress varied as 590, 756, 878 and 1010. So, these are the observations from the suction control tests on a given soil, and here 4 different matrix suctions are maintained and the tests are conducted. Then this data, if you plot it on y axis Q and x axis P, so at saturated state you may have data somewhat like this, and this is what you obtain here. So, this is the data that is given to you, and we need to obtain C phi, the cohesion intercept and angle of internal friction for all the 4 sets of data. So, from the first set of data, that is test 1 and 2, if you take, so 130, 120 is equals to 130 tan phi dash plus C dash, and 274 is equals to 350 tan phi dash plus C dash. When you solve this, you get phi dash is equals to tan inverse of this is 35 degrees. So, when you substitute this into any of these equations, you get C dash is equals to 29 kilopascal. So, this is 29 and the angle is 35 degrees. From the test, even test 3 and 4 if you take, you should get the same data. You should get same C dash and phi dash, and test 5 and 6 if you consider. So, you have 363, 370 tan phi dash or phi 1 dash. We do not know whether its phi dash is same as phi 1 dash. So, you can assume it is different, then when you compute the phi 1 dash we can compare with phi dash. So, this is C 1 dash and 210 is equals to 150 tan phi 1 dash, because these are all conducted at the same matrix suction values C 1 dash. When you solve this, phi 1 dash is equal to tan inverse of which is equals to 34.8 degrees, which is nearly equals to the phi dash, that is 35 degrees. When you substitute into the above equations, you get C1 dash as 104 kilopascal. Similarly, from test 9 and 10, phi dash is 35 degrees, and C2 dash is equals to 198 kilopascal. And test 13 and 14, phi dash is 35 degrees again, that is phi 1 dash, phi 2 dash, phi 3 dash, 35 degrees, and C3 dash is 423.3 kilopascal. Now, knowing the intercepts for different matrix suction values for the data under controlled matrix suction values, now we can obtain the suction stress. The suction stress values sigma s. So, let me write this somewhere here, test 1 and 2. So, sigma s values we can obtain. Sigma s is equals to nothing but C dash, C I dash by tan phi I dash. So, this is sigma s axis, and when this is extended onto the negative axis, this point is C dash by tan phi dash. So, C dash by tan phi dash for this value is 41.4 kilopascal, and for the second set of data, this is C1 dash by tan phi dash. C1 dash is 104 by tan phi dash is 35. This is 148.5, and for the next set, so this is again C2 dash by tan phi dash. So, this data is 198 by tan 35. This is equals to 282.8 kilopascal, and similarly for the last set of data, cohesion intercept is 423.3 by tan 35. This is 604 kilopascal. So, we have the sigma s data, therefore, now sigma dash effective stress is equals to sigma T minus UA, this is net normal stress, plus sigma S dash plus sigma C naught. So, this is initial cohesion, this together is sigma S, that is what we got now. So, therefore, the effective stress is sigma total minus UA plus sigma S. These values we have, and net normal stress values we have, therefore, effective stress values we can obtain. For the previous data, we can write here itself, the sigma dash is here effective mean stress, therefore, this is simply P dash. So, P dash value is 130 plus 41.4. So, this is 171.4 and this is 350 plus 41.4, therefore, this is 391.4, 561.4, 736.4. For other values, so now we have mean effective stress and Q. So, that is deviatic stress. We can plot deviatic stress versus mean effective stress. If you plot, you will get data like this, a unique failure envelope using different data. And similarly, we can plot sigma s and u minus uw. So, we get data somewhat like this. So, this is the SSCC, suction stress characteristic curve. So, here the true effective stress for a given unsaturated soil can be determined from the routine suction control tests. And once the suction stress characteristic curve is obtained from the deviatic stress versus net normal stress data from the suction control tests, we can compute the cohesion intercepts and angle of internal friction values, and from the cohesion intercepts one can obtain the suction stress directly. From the suction stress one can compute the effective stresses or effective mean stress. So, the deviatic stress versus effective stress can be drawn and a unique failure envelope can be obtained. Thank you.